Can you hear me now? Okay, let's get started. Seems like we haven't lost everyone during the break. That's good. Did you guys have a good break? Yeah? Okay, good. So hopefully you're all refreshed. Just like the DRAM cells, you need to refresh also. So hopefully you're all refreshed to study more. Okay, we're going to continue where we left off last time. Remember, we started the microarchitecture and we designed a single cycle processor. And we're going to do more. We're going to do some more analysis, finish the design first, and then do an analysis, and then motivate better microarchitectures. So a lot of what we will cover going forward will be concepts that are employed in most modern processors. Okay, let me start this over here. Okay, this week, this is what we're going to cover. Next week, we're going to start with pipelining. Okay? So hopefully you're doing the readings. So after a few lectures, you won't have as many readings, unfortunately, because the books are not up to date. I'll be very frank. There aren't a lot of up-to-date books in the field today that cover the advanced concepts. You really need to have 10 different books, and some concepts are not even covered in books in the level I'm going to cover. So I think starting with maybe this lecture over here, maybe the lecture after that, you will not have a lot of information in the textbooks that you're assigned. So the lectures will be the main material that you will have. But to be able to understand everything, I would really recommend that you do all of the readings that we have in the past. Okay, so this is where we are. You've covered this stuff over here. We're kind of in the middle of microarchitecture. We're going to cover multi-cycle and microprogramming, hopefully by the end of this week, today and tomorrow. So recall, just to jog your memory, what we were talking about. We were talking about a single cycle microarchitecture. What does this mean? This means that every instruction takes a single cycle, single clock cycle to execute, which means that only combinational logic is used to implement instruction execution. Because if you have sequential logic, you need to latch the data. That by definition makes it multiple cycles, right? At the end of the clock cycle, you latch the data. So there are no intermediate programmable invisible state updates. We're going to fix that at the end of this lecture today. So this is another view. You have the architectural state at the beginning of a clock cycle. You process the instruction in a single clock cycle, and then you get the architectural state prime at the end of the clock cycle, reflecting all the updates that are supposed to be done by that instruction according to the specification of the instruction set architecture. Okay, so this slide you should be familiar with. And this is a very abstract view of a single cycle machine. It's essentially this, basically. You have the architectural state stored in the sequential logic, and the state gets updated in a single cycle through this combinational logic, and you get architectural state prime. Make sense? And I've asked you these questions. I'm going to ask you those again. What is the clock cycle determined by, and what is the critical path of the combinational logic determined by? Clock cycle is always determined by the longest critical path delay within this combinational logic, plus the setup and hold time, as we've discussed in the timing lectures. But we're going to look into that a little bit more later in this lecture. Again, to jog your memory, remember to design this, you need sequential logic elements as well as combinational logic elements. These are our sequential logic elements. Again, this is recall. This is from a previous slide earlier. And these are our sequential state elements. And this is architectural state in this case. And this was the single cycle MIPS data path we designed. This is the data path. How do you do the updates of the, what is the combinational logic that you need to do the updates of the architectural state? You see the state elements inside here, but you also see a bunch of data path elements like muxes, the ALU, the address calculation adder over here, and a bunch of shifting logic, sign extension logic to implement the instructions. And if you recall, in the last lecture, we went through almost every single instruction that is important to us in this course and derived this data path. This is the result of the last lecture, okay? We didn't talk a lot about control over here, so today we're going to start with the control logic. How do you design it? It's relatively easy, actually, because once you implement the data path, you just need to control it to make sure that it's doing the thing that is specified by the instruction. In a single cycle machine, the control is relatively easy. Basically, you need to do what the instruction tells you to do in a single cycle. That's it. The ISA specification says the instruction should do this. You ensure that the data path elements are controlled such that the instruction produces that result. Makes sense, right? It's very simple. Which means that you need to implement what the instruction is supposed to do as a combinational function of that. Basically, instruction is at the memory location specified by the program counter. You need to get those bits of the instruction, and the bits you get depend on the type of the instruction. And you need to decide the control signals that are controlling the data path based on the bits that you get from each of the instructions. It's clear, right? Okay, so I'll go back to the data path over here. And then we will, basically this is the control logic. See, over here it takes the instruction, right? Actually the top 6 bits of the instruction, which determines your opcode, and generates these control signals. And there's also some more control over here, which is the ALU control. This tells you what ALU operation you should do, depending on the type of the instruction. And there are a bunch of other control signals that are generated during the operation, in the combination logic itself over here, not just directly from the instruction, but from the combination logic. We will see each of these signals over here. But basically, you need to consider all of the instructions that you're implementing and decide the control signals based on that. So let's take a look at these. These are the list of the control signals in the previous picture that I showed you over here. I wish we had 2 screens over here so that I could switch between these 2 different things, but unfortunately our room is not capable of that, at least at the moment. So I'll have to switch between the slides. I know some of you do not necessarily like this, but we'll need to switch. Okay, so this is the register destination. So this means that we're going to, this is the destination register ID of the instruction that is going to write to a register. So, so if you go back to the reg dest over here, I'll try to find it over here. No, I cannot find it. This is it. Yeah, this is the reg dest over here, as you can see. Basically, this control signal decides which input this mux should pass. Should it take the bits 20 through 16 of the instruction as the destination register ID, or should it take bits 16 through 11, 15 through 11 of the instruction as the destination register ID? And this, if you remember, depends whether the instruction is R-type or I-type. Depending on that, your destination register comes from here or here, right? That's essentially what we do, basically. You deassert the signal if the instruction is writing to a register that's specified by 20 through 16. Otherwise, you assert the signal. And the equation can be simply determined by looking at the opcode. If the opcode is 0, then you're writing to 16 through 11. If the opcode is not 0, this is a non-zero opcode over here, then the instruction is supposed to be writing to a destination register that's specified by 20 through 16. That's why you set the control signal based on the opcode equals 0 comparison. Make sense? So you need a comparator that compares the opcode to 0. If the opcode is 0, I'm going back again. If the opcode is 0, then the destination register is this one, actually. If the opcode is not 0, then the destination register is this one. Okay, makes sense, right? Okay, we're going to see more examples of this. And you do the same thing for all of the control signals. So let's do another one. Reg write is a very easy one, right? Are you actually writing to a register? You disable the write if the instruction is not writing to the register. You enable the write, enable the signal, set it to 1, if the instruction is supposed to write to the register. So all of the opcodes that are writing to the register enable this signal. So if the opcode is not store word, and it's not branch, and it's not jump, and it's not jump register, these are the instructions that do not write to a register, then the signal is set to true. Everything else writes to a register, which means that your register write signal should be set to 1. So let me go back again. Register write signal is over here. It's basically the write enable signal for the register file. And you should set it only if the instruction is supposed to write to a destination register. Makes sense, right? Simple. Basically, you need to go through, after you design your data path, you need to go through every single control signal and decide when it should be a 1 and when it should be a 0. And to be able to do this, you need to go through the specification of the ISA. As you can see over here, another example over here. Let me not do the mem to reg. It's not that easy. Well, it's easy actually if you know the data path, but let's do the mem read. Mem read is a very simple one, right? If the instruction is supposed to be reading from memory, from the data memory, then this signal is enabled. Otherwise, it's disabled. In this case, it's only opcode, only load word is reading from data memory. Memwrite is another one. If the instruction is supposed to write to the memory, opcode equals store word, then this signal is enabled or set to 1. Otherwise, it's set to 0. ... Basically, you need to go through every single signal and make sure that you set it correctly, depending on which instruction is supposed to use that particular signal in a particular way. And I think this table, you can study it on your own. I'm not going to go through every single signal over here. This is a simple machine, but even in this simple machine, you can see that there are 4 bits plus 4 more bits, 8 control signals, controlling the different muxes and controlling the registers and memory. Make sense? Okay, so there's also ALU control. These are additional signals, but in this case, it's relatively simple. Here, ALU control is determined by the opcode, basically. If the opcode is 0, then the operation is selected according to the function. So let's go back to these instructions. You have to always know the instructions. So if the opcode is 0, then what you're doing with the instruction is determined by this function. This is an R-type ALU operation. So this function directly determines what your ALU is supposed to do. If your opcode is not 0, then you have different cases for the opcodes. If it's an ALU immediate, you select the operation according to the opcode itself. If it's a load word, you select addition because load word computes address based on base register plus immediate, right? Sign extended immediate. Store word does the same thing, so ALU control should be an addition. And for branches, you select branch condition generation function. And again, you need to go through the data path to understand that. If the opcode is not any of these, then it's a don't care. You don't care what the ALU is doing because you're not going to lash the result into a register or memory. So let's go back to this picture again. So if you look over here, this is the ALU control. So you need to design this control logic as well. There's control logic here, and there's control logic here that basically controls the ALU. You can think of this as a hierarchical control mechanism, right? You get some signals from here that are fed to this other little controller that controls the ALU. And this big controller controls all of the other muxes in the system. Muxes plus whatever other thing that it's supposed to control, like the register writes or memory read signals. Okay. So these are the example ALU operations. And in the last lecture, we actually went through an ALU design that implements these operations. So you can take a look at those. Okay, so this is basically simple. It's the control logic. Now let's control this data path a little bit. Let's do some concrete examples. This is our data path. The orange ones are the control logic. Let's look at R-type ALU operations. For R-type ALU operations, you need to set the control signals this way, which means that, as you can see over here, the instruction gets decoded. In an R-type ALU operation, the destination register is supposed to be specified by bits 15 through 11 of the instruction. So you need to ensure that this mux connects this input to this write register ID. So you need to set the signal to 1, as you can see, this control signal. We're going to read a register. It's an R-type operation. It adds 2 registers, or it does operations to 2 registers, which means that the second operand going into the ALU is coming from the output of the second read port of the register file. So you need to ensure that this mux is connected this way. The register file output is connected to the ALU. Okay, sorry. And you need to ensure that the ALU is doing the correct operation. Remember, the ALU is specified by function. In an R-type operation, the opcode is 0, and funct itself, the bottom 6 bits, determine what your ALU is supposed to do. So in this case, we directly put funct over here. There's additional control logic inside there, but you can design that. That's not that hard. In an R-type ALU operation, we're not reading from memory. Well, this is the memwrite, sorry. We're not reading from, we're not writing to memory. So we get 0. We're also not going to read from memory, so we're going to ignore the output that we get from memory. Essentially, the data that we're going to write to the destination register should come from the ALU result. So this data path should bring the ALU result through this mux to the input of the register file. I lost my mouse. Yeah, there you go. So basically, ALU result should flow through this mux to the data input of the write register over here, destination register. So this mux should be set to 1, which means that we're actually getting the ALU result to the register file and not the memory result to the register file. That's why the signal is aptly named memory to register. We're not setting the memory to register to 1 because we're actually taking the ALU result as selecting, this mux is selecting the ALU result as its input to pass. Okay? So those signals are done. What else do we need to do? We need to write to the register clearly, because then every R-type ALU operation writes to a register. You need to set the control signal reg write to 1 so that the register file is written to. And we're not done yet. We need to update the program counter. Now this is data path. This is the data path we designed. The program counter needs to get PC plus 4, essentially PC plus 4, because we're not changing the control flow, right? The next instruction is the next sequential instruction. So how do we get PC plus 4? You have PC here plus 4. That data needs to flow this way. And we should not select this one. This is used by branches. So we should select the mux. The control of this mux should be 0, such that it passes the PC plus 4. And the control of this mux should also be, in this case, 0, such that it passes PC plus 4 over here, such that that goes and gets lashed to the program counter at the end of the cycle. Make sense? So we're not selecting the inputs of these muxes. Okay, so that basically, we've controlled the data path for every R-type ALU instruction by switching the muxes this way, as I've shown over here, and setting the control signals of the memory and the registers this way, and setting the control signal of the ALU this way. So once you've designed the data path, it's really easy to select your control signals. Any questions? It's hopefully simple, right? So you need to do this for every instruction now. Your data path was capable. We designed the data path such that it was capable of executing every single instruction. Now we need to do the control logic accordingly, such that we're capable of correctly executing every single instruction. Now let me give you the I-type ALU also very quickly. The difference between R-type and I-type, take a look at the screen, is going to be this. As you can see, this was R-type, and this becomes I-type. Only these muxes change, as you can see, right? I keep doing this. So this is I-type. I-type means the destination register comes from instruction bits 20 through 16. So we select this input of this mux, and it's immediate. The second source operand is not a register, it's sign extend immediate. So we should put the sign extended immediate coming from the instruction bits as an input to the ALU, so that we can do an immediate ALU operation. And everything else stays the same control signals as the R-type. Okay, load word. It is similar. I can go through all of these one by one, but it becomes boring relatively quickly. In load word is actually relatively similar to I-type, as you can see. Yeah, basically, the destination register is specified by this one, and we need to compute the address over here, very similar to an I-type instruction. And in this case, we want to read the memory because it's a load instruction. So we should select the output of memory to be passed, to be input to the destination register of the register file. And load word also writes to the register file, so reg write signal should be 1. And load word doesn't change the control flow, so PC should be selected to become PC plus 4. Okay, so we're controlling the data path such that it does the right thing for every single instruction. Data flows correctly, and it updates the state correctly for every single instruction. For load word, you can see that the ALU operation is add, because we're adding base register plus sign extended immediate inside the ALU to compute the address. Store word is very similar to load word, except we're not reading from memory, we're not writing to a destination register. So this was load word. Store word, we're not writing to a destination register, so reg write signal becomes 0 over here, as you can see. And we're not really reading from memory, so we don't really care what this mux does, because we're not writing to the destination register. And because we're not writing to the destination register, we don't really care what this mux does. But we are writing to memory. So we're going to read the data that comes out of the register file and write to memory over here through this address. Oh, sorry. Okay, we're going to read the data that comes out of the register file. This is directly supplied over here. There's no control over here. But we control the memory write signal over here, set it to 1. And the address needs to be determined this way. Base register plus sign extended offset. Very similar to the load word address determination. So we need to set this mux to connect the sign extend immediate to the ALU. And the ALU operation should be an addition, as you can see over here, because that's how we calculate the address for store word. Okay, now we're going through every single instruction. Maybe I'll leave the branches to you so that you can have fun with them. But branches, I'll give you the high-level idea over here. Branches are not writing to a register, so the register write signal should be 0. They're not writing to memory, so memory write signal should be 0. Since we're not writing to a register, we don't really care what this mux does, because we are ensuring that write enable is not set for the register. We don't really care what this mux does, because that deals with data flow into the register file, and we're not flowing any data into the register file. But we need to compute the branch condition accordingly. For this to happen, in this case, it's a not taken case, but the branch condition computation signal should set the ALU accordingly. And you should take a look at the past slides to determine. This depends on what the branch is. If it's a branch equal, you subtract the source register from the destination register. You need to ensure that the source register is supplied to the ALU, and the destination register is also supplied to the ALU, right? And you can see that it is supplied to the ALU. So let's assume that this branch is not taken. Not taken means that ALU outputs a signal saying, oh, this branch condition does not hold. So that signal is gated with this thing over here, this branch signal. If the branch is true and the branch condition holds, then we're going to take this output of the ALU. This is the branch destination target address computation logic over here. So in this case, I say not taken. Take my word for it. If the branch executes at not taken, as not taken, this will be set to 0. Even though this is a branch, the branch condition will indicate that, oh, we're not going to take the branch. For example, if the branch is branch equal register 5, register 6. If register 5 is equal to register 6, take the branch. Assume that the values of register 5 and register 6 are not equal. One is 0 and the other is 1. Then the ALU computation would result in a 0 over here. And even though this is a branch, this AND gate will output 0, and we will take this input to this mux. And we need to ensure that this is not this signal is set when this is actually a jump, because this is actually the jump computation logic. So we basically pass PC plus 4 to update the program counter for a not taken branch. Makes sense? Now let's take a look at the taken branch. Okay, so let me do the taken branch, and then I'll go back to that point. If you do the taken branch, the branch condition will say, oh, branch condition is taken, so this is a 1. So, and this is a branch, so you'll get a 1 out of this, and this mux will select the input coming from the branch target address computation logic over here. And that's how you get branch target address into the PC. Only if the branch condition holds over here. Now, this is an interesting control signal. We're controlling muxes not only based on what the instruction is, but what the result of the instruction is, intermediate result of the instruction is. So basically, some control signals are dependent on the processing of the data. In case of a branch, we just saw this. If the branch is taken, if the branch is not taken, this control signal should be set to 0. If the branch is taken, this control should be set to 1, such that we get the correct program counter latched into the PC program counter register at the end of the clock cycle. So you will see that there will be more and more signals that are dependent on the processing of the instruction. There are two types of signals. Some of them are not dependent on what's happening in the data path. You generate them based on the instructions. Some of them will be dependent on what's happening in the data path. And this is one example signal. Okay. So jump, I'll leave you with the jump. Jump is actually really easy. All you need to do is nothing over here, because jump is an unconditional jump. You just need to compute the target address and ensure that the PC is updated with the target address. And that's essentially this. This is the jump target address computation logic. And you need to connect it to the PC with this mux. And everything else can be don't care as long as you're not doing any harm. Meaning that you're not writing to the register file, that should be 0. You're not writing to memory, that should be 0. Everything else can be don't cares. Okay? Okay, I think we've gone through every single instruction that I wanted to go through. So hopefully this is very clear how a data path is controlled. Okay, so what's in this control box? I didn't tell you exactly how to implement it, but I think it should be obvious right now because logically you know what to do. Now you need to bring it down all the way to logic circuits. So it could be combinational logic. So in this case, in a single cycle machine, it has to be combinational logic actually. It doesn't really have to be, but keep it that way for now. Basically, this is hardwired control. Control signals are generated combinationally based on the instruction, plus some other control signals that come due to processing. This is usually necessary in a single cycle microarchitecture. On the other hand, we will see in the next lecture that we could do this control block as sequential logic. This is called sequential or microprogram control, and you will understand this much better. But this is basically a memory structure that contains the control signals associated with an instruction. We will index this memory structure with some address, and it'll give us all the control signals that we want to control the data path elements. That sounds beautiful, right? That's a sequential control logic. And we will see that in the next lecture. You don't need to worry about that at the moment, but this is called a control store. Okay, so this is essentially our complete single cycle processor. Now we've covered the data path. We've also covered the control logic. Now everybody knows how to design a single cycle processor? Yeah, more or less. Well, you never know how to design it before you design it. That's why you'll design it, essentially. Okay, so this is one example. This is one microarchitecture. We've implemented a subset of the MIPS ISA this way. We could have chosen a different implementation. I'm not going to cover a different implementation of a single cycle microarchitecture. Even the single cycle microarchitecture can have multiple different implementations, but your textbook has a different implementation. I'll cover very quickly what your textbook has, and I'll have some slides. There are some backup slides to reinforce the concepts. You will see that they're going to be very, very similar to what we've just discussed, with very minute differences, perhaps. The signal names are different, but even those are very, very similar to each other. But I will definitely recommend that you should do the readings to follow everything. But basically, this is the complete single cycle processor from your textbook. It looks very similar, right? Maybe it looks better drawn, I'm not sure. Maybe it doesn't have all the instructions over here, but it has this control block over here. It has this PC source signals that we've also looked at. It has this PC muxes, ... So let's take a look at how you do the load over here relatively quickly. It's going to be very similar to what we've done. You need the state elements. These are the state elements: program counter, instruction memory, register file, data memory. Looks the same. And we're going to go through the single cycle data path for load word. Basically, we need to have the step for fetching the instruction. You input the program counter, you get the instruction over here. The next step is read source operands from the register file. You need to have the data path connections for that. The next is enabling load word immediate. You need to sign extend the immediate so that you can compute the address, right? Because we want to have the base register plus the offset. The next step is computing the memory address by adding the base register to the offset. And you need to set the ALU condition correctly for this to operate. And the next step is actually reading from the memory and writing the data back into the register file by setting the control signals accordingly. We've just formed the data path just for the load word instruction in a very similar way we did for the previous processor, except this is in your textbook, so you can read this in more detail. And we are not done yet, of course. We're not, you need to increment the PC, right? You always need to ensure that the specification of the ISA is obeyed. And the specification of the ISA says that you increment the PC, so you need to add the data path elements to increment the PC. Okay. And of course, now you need to add the other instructions to form the data path. That's what gets you to this more complicated data path. That's where I'm not going to go back in the slides, but I'm going to show you over here. Basically, this is a single cycle microarchitecture in your readings. I just showed you 5 slides ago the picture. And it needs to have control logic. And your textbook talks about how to generate the control logic. And this is one example. This is the control unit of, and you can see that it's in the chapter 7.3 of the textbook. If it's an R-type instruction, let me go through the R-type because we just covered the R-type in a little bit more detail. If it's an R-type instruction, the opcode is 0. You're writing to a register, that needs to be set to 1. Register destination mux needs to set one, remember, are you getting the destination register ID from bits 20 through 16 of the instruction or bits 15 through 11 of the instruction? This needs to be set accordingly. ALU source needs to be set to 0. We're not branching. We're not writing to memory. We're getting the result not from memory, but from the register. So mem to reg, memory is not connected to the register file. That's why this is 0. And ALU op should be specified by essentially the function over here. You can read this in more detail based on the ALU design in the book. And this is not a jump. So these are all the control signals that you need to set to execute an R-type operation correctly in this data path over here. And you can convince yourself by going through this data path and studying it. But it's going to be very, 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 very similar to what we've just done a few minutes ago for the other data path, which is very, very similar. Okay, any questions? Okay. Basically, what I've shown you, the reason I wanted to cover these two slightly different data paths is to show that you have a single cycle microarchitecture. You're designing these things slightly differently, but they're going to be very similar. Again, I'll cover this. This is a single cycle microarchitecture that we've developed in the last lecture and today. And this is the single cycle microarchitecture in your readings. And if I flip between these two, they actually look very similar also. Even some of the signal names are very, very similar. So now we're done with the single cycle microarchitecture. Now let's take a look at, is this a good idea? You're going to do this because this is really important to do so that you can understand the concepts, but hopefully you'll be convinced that this is not a good idea. This is not a good way of designing machines. Nobody does things this way, but you need to walk before you run. That's why we cover it. So let's evaluate it. There are multiple questions over here. Is this a good idea? Is this a good design? When is this a good design? These are rhetorical questions at the moment. When is it a bad design? You should always think about, are there cases when this is a good design and when this is a bad design? Usually this is a bad design, but there may be cases where this is a good design, and we'll talk about that later on. How can we design a better microarchitecture? So actually all of the rest of this lecture, the rest of this course will be about this. How can we design a better microarchitecture? Now, we will talk about other concepts, but a lot of what we'll cover will be better microarchitectures. So to be able to do this right, let's talk about performance analysis a little bit. I've covered this in the last lecture slightly, actually with one slide. We've talked about it a little bit. But do you remember the performance equation? How long it takes to execute a program? It's a function of three things. The number of instructions you have in the program, the number of cycles it takes to execute each instruction on average, and your clock cycle time. How long is your clock cycle? If you multiply these three things, you will get the execution time, how long it takes to execute a program. This is also called the iron law of performance analysis. But we're going to go through this. These slides actually are going to summarize what I just said in more words. So basically, every program consists of a series of instructions, and each instruction needs to be executed clearly. So if you want to figure out how fast is your program, you need to look at how fast is each instruction, right? Each instruction is clearly realized on the hardware. And we've seen two example single-cycle microarchitectures that realize the hardware. They can take one or more clock cycles to complete, even though so far we've seen only microarchitectures that can execute an instruction in a single clock cycle. So that's what cycles per instruction means. How many cycles does it take to execute an instruction? You've seen examples of only one. Cycle per instruction in a single cycle microarchitecture is set to 1. You don't change it. That's by definition. Okay, but then there's also another part of the performance equation, which is how much time does one clock cycle take to execute? And in this case, remember the questions I asked earlier, the critical path of the maximum combinational logic delay determines how much time one cycle requires. This is called the clock period, and the inverse of this is the clock frequency. How many cycles can be done each second? These are basically inverses of each other. So if you have a 1 gigahertz machine, it means that a clock cycle is 1 divided by 1 gigahertz, right? Essentially 1 nanoseconds. One clock cycle is 1 nanoseconds in that case. So basically, if you have a program that consists of n instructions, and the processor needs cycles per instruction, cycles for each instruction, average, and the maximum clock speed of the processor is f, clock period is t equals 1 divided by f, This is the performance equation that I just told you earlier. N times cycles per instruction times 1 divided by F, or N times cycles per instructions times T seconds. T is the period, clock period. Okay. So remember, this slide is actually from the last lecture, almost. Execution time of an instruction. Look at, if you think about it another way, execution time of each instruction is cycles it takes to execute that instruction times the clock cycle time, and we already defined this. The execution time of the entire program is really summing all of this over all of the instructions. Cycles per instruction times clock cycle time, summed over all of the instructions. That's why we get this equation over here. N times CPI times T in the previous slide, clock cycle time. Do not forget this. So if you look at a single cycle design, this is going to be always 1. Average is 1, worst case is 1, every case is 1, actually. Cycles per instruction is 1. So you can change the number of instructions, but that leads to other issues. But you have only one level of freedom, clock cycle time, right? So it's good to think about how do you optimize the performance of a program at this point. You can change the number of instructions, but you don't do that after the program is compiled, right? You already have a given number of instructions to you. If you want to change the number of instructions, you need to do some other thing. You need to change the algorithm, for example, or you need to change your compiler. Or you can change the cycles per instruction. In a single cycle design, you don't have that freedom. That's always 1. Or you can minimize your clock cycle time. So the best thing you can do as a microarchitect designing a single cycle machine is minimizing your clock cycle time. So you're very restrained in what you can do. Okay, so let's do the performance analysis of our single cycle design. As I said, each instruction takes 1 clock cycle to execute. That's obvious. How long each instruction takes to execute is determined by the slowest instruction now. Because every instruction takes 1 cycle, the slowest instruction determines your cycle time. That's the answer to the question earlier. Even though many instructions do not need that long to execute, right? Some instruction, like the jump that we've seen, doesn't really need to go through reading a register, reading memory, doing something in the ALU, writing the result back into the register file. That's a very long process. Jump just calculates the address and updates the program counter. It doesn't matter. Jump will take the same clock cycle time to execute because you have only a single cycle to execute every single instruction. You don't have freedom. So basically, clock cycle time of the microarchitecture is determined by how long it takes to complete the slowest instruction. So if you want to analyze the performance of a single cycle machine, you'd better figure out how long it takes to execute your slowest instruction. Which means that you need to find the critical path of the design, of the combination logic, based on the processing time of the slowest instruction. Okay, so what is the slowest instruction to process? Now we have this question at hand. We need to go back to the basics and figure out what is the slowest instruction in the microarchitecture we designed. Of course, to be able to do this correctly, you need to design your microarchitecture and know exactly what the delays are, right? Go back to lecture number 7, I think, or 8, lecture number 8. That's timing and verification. That's where we did the combination logic delay analysis, right? You need to do that analysis. But let's do that analysis at a relatively high level. I'll give you some numbers so that we can do this analysis. Basically, we have 6 phases of the instruction processing cycle, and all of these need to take a single machine clock cycle to complete. We need to go through all of this. I'm going to reduce this to 5 phases to make things simple in our example design. One of the key questions is, do each of the above phases take the same time for all instructions? That's not true, right? So let's find the critical path in this design. I'm going to give you some numbers over here. Assume for the design in this slide, we're going to assume these things. Basically, instruction fetch, memory units, read or write takes 200 picoseconds, ALU and adders take 100 picoseconds, register file read or write takes 50 picoseconds, and we're going to magically assume that all other combination logic is free. 0 picoseconds. It's not realistic, clearly, based on what we've learned in lecture 8, but let's simplify the problem. Now, what we need to do is we need to go through all of these steps for all of the different types of instructions that exercise the steps. For R-type instructions, we go through instruction fetch. We need to decode them, access the register file. We need to do an ALU operation. There is no memory stage. We bypass memory. And because other combination logic delay is 0, assumed to be 0 over here, we get 0 over here. And we need to write to the register file. So if you look at the R-type instruction, its delay is 400 picoseconds. Now, jump, as I said, is only 200 picoseconds, right? But on the other hand, load word, in this case, is about 600 picoseconds because it exercises all of the stages over here. It needs to read the instruction from the memory. It needs to read registers from the register file. It needs to do an ALU operation to calculate the address. It needs to read data from memory. It needs to write the data that's read from memory into the register file. So that's 600 picoseconds, which means that our critical path is this. Even though jump instruction doesn't need to take 600 picoseconds, it has to take 600 picoseconds because we have only a single clock cycle to execute every single instruction. So let's find the critical path. Let's play this game a little bit. So if we go through the R-type and I-type ALU, these are two possible critical paths. This is the critical path that goes through reading the register, doing the ALU operation, bypassing the memory, and writing the result back into the register file. That's 400 picoseconds. There's another potential critical path, which is updating the program counter, but that's really fast, 200 picoseconds over here. So the real critical path for R-type and I-type ALU is this one. For load word, this is the longest. As you can see, we exercise all of the structures as we've just discussed. That gives you 600 picoseconds. That's the critical path. Another potential critical path is this one, but this is usually very slow, very fast, because you don't need to go through a memory or even ALU in this case, right? This is just PC equals PC plus 4. Okay, store word. Store word goes through memory, but it's not as slow as load because it doesn't write to the register file, right? As you can see over here. This path is not exercised. As a result, the critical path delay of a store word is 550 picoseconds. Let's look at branch taken. Branch taken actually has two critical paths. Both of them could be critical paths. One is over here. You get the output of the ALU after 350 picoseconds. That's the branch condition. Is it taken or not taken? That affects the output of this mux. There's another thing that affects the output of this mux, which is PC equals the target address. Basically, the target address computation logic, right? This one over here. It turns out this takes only 200 picoseconds. This takes 350 picoseconds. So this is really the critical path. And then you need to update the program counter. We assume magically that that's 0 picoseconds. So you get 350 picoseconds. Make sense? So you need to carefully do the critical path analysis because there may be multiple potential critical paths in a combinational logic as we've discussed in lecture 8. Jump is the easiest one. As you can see, it's potentially, again, has two potential critical paths, but it turns out it's just 200 picoseconds, and you can do the analysis yourself over here. Okay? So that's what we've done. Essentially, the slowest instruction determines your critical path. You can ask the question, what about control logic? We didn't do the analysis for the control logic except for the branches, right? For the branches, we did the analysis because the branch conditions are determined by data path, but also control logic generates some signals. If the control logic is too slow, it can affect your critical path. I didn't do that analysis, but this is going to be food for thought for you. Usually, in most modern systems, if you're designing it well, your control logic should not be on your critical path. This box over here, if you design this and it's on your critical path, you have a problem. You've done something wrong. I will argue that. And in most real systems, control logic is not on the critical path, unless the control signal is generated based on the processing that's done in the data path. For example, whether the branch should be taken or not taken, that's done, that signal is generated based on the processing that you do in the data path, right? You compare two registers, for example. Okay? But otherwise, your control signal should not be on your critical path. And we will see later on caches, cache hit-miss signal. That's usually on the critical path on many processors, actually, because you need to access a data path element that needs to tell you, oh, I have the data or I don't have the data. And now you need to make a decision as to what to do. So historically, actually, there have been machines where control logic has been on the critical path. Control Data Corporation had this machine, 5600. Before their flagship processor, it turned out control store took too long to access. We'll talk about the control store in the next lecture. Okay, so let's go through this exercise. I want to finish a few things before we take a break, going to the system design principles. But let's finish this. What is the slowest instruction to process? Let's put some more thought into it. So load word, we found that load word is 600 picoseconds, right? This is actually not an unreasonable thing. In most machines today, if you look at Intel processors, that could be your critical path. Load is a very tough instruction to process because you need to do a lot of things. Even if you break it into multiple cycles, it takes a long time. But load actually has another very big downside. We've assumed magic memory, right? We assume you can access memory in a single cycle, and you get the data back. Not even a single cycle. It's really combinational, right? I said memory access takes 200 picoseconds. That's not true in existing machines. Remember, we drew this picture in one of the earlier lectures where we said memory actually takes a long time to access. Well, what if memory sometimes takes 100 milliseconds to access? It could, because you may actually need to access your disk and it is contended, whatever. So now you have a problem with your single cycle microarchitecture. It sucks, right? Why? Because your longest instruction now takes 100 milliseconds plus all else to do a memory operation. And you're forcing every single instruction to take that long. Even your jump instruction, right? Not good. And what if you need to access memory more than once to process an instruction? This is usually a good question to ask. Are there any instructions that do not require access to memory? Anybody who wants to answer? Can you give me one instruction that doesn't require any memory access? Yes? Jump doesn't require, that's true. But I tricked you. I tricked you because I asked the question a particular way. A jump doesn't require memory access, but it requires a memory access to be fetched. So that's the trick part of the question. There's no instruction that does not require memory access. Every instruction needs to be fetched from memory, which means that every instruction needs to access memory. And if your memory takes sometimes 100 milliseconds, that's too bad, right? So, okay. So do you provide multiple ports to memory? That's another question, right? Because you need to be able to access the instruction from memory, and you need to be able to access, for a load word, you need to be able to fetch the load word, the instruction itself from memory, and you need to be able to fetch the data that it requires from memory. Now, do you require 2 ports to access memory, or 2 copies of memory to service a load instruction, to execute a load instruction? Remember, we're doing everything in a single cycle. You should have all of the combinational signals stable for the entire clock cycle for the load word to execute, which means that you should be accessing the memory to get the instruction all the time during that clock cycle. Also, you should be accessing memory to get the data. So you definitely need 2 ports. But I cheated, and all of the books are cheating, in a sense. They're assuming 2 different types of memory, right? Instruction memory and data memory. So you have 2 different types of memory that you can access for different reasons. Okay. Okay, basically, what I'm getting at is the single cycle microarchitecture is actually, even though it looks simple, it's a very complex architecture to build, microarchitecture to build in real life. Because it's very contrived, first of all, it's not intuitive. All instructions run as slow as the slowest instruction. I hopefully just convince you that the slowest instruction is really, really slow, in a modern machine especially. It's inefficient because of the same reason, but because of one other reason. You must provide the worst-case combinational logic resources. I don't know why that's flickering over there. You're not seeing the flicker over here, right? Okay, this is fine, but somehow that one's flickering. Not good for the people in the other room. But basically, you must provide the worst-case combination resource in parallel as required by any instruction. If the instruction requires 2 accesses to memory, you need to have 2 types of memory. If the instruction requires to do an address computation and something else, branch condition computation, you need to provide 2 adders, 2 ALUs. That's actually expensive real estate. Whereas if you did things in multiple different cycles, then you could get away with a smaller and simpler design, as we will see. So you need to replicate a resource if it's needed more than once by an instruction during different parts of the instruction processing cycle. We just saw that for load word. You need to have a memory to fetch the instruction, you need to have a memory to fetch the data of the instruction. So 2 ports to the memory. So as a result, this is not necessarily the simplest way to implement an ISA. And actually, there are much more complicated instructions than what we've dealt with so far. Repeat move S is one of my favorite examples. this instruction exists in the x86 architecture. What it does is it essentially does a string copy. It copies a string of arbitrary length. The length is encoded in a register, counter register. So its size, I assume, could be 2 to the 32 in a 32-bit architecture. It copies a string of that length that's provided in the count register from a location that's pointed to by this address to a location pointed to this address. So it does byte by byte copying. It takes the byte from this location, copies it to this location, and checks, am I done yet? Is the count register 0? If not, it decrements the counter. Then it goes to the next byte. Copies that byte from this location to that location. Checks, am I done yet? Is the count register 0? If not, decrement the counter, do it again. Keep doing it again. Basically, it's a loop, string copy loop, implemented by a single instruction in the instruction set architecture. Imagine doing this in a single cycle. Good luck, right? You're not going to be able to do this. I'm not going to talk about index instruction, but this actually enables indexing in a multi-dimensional array in a complex instruction set architecture. Okay, so basically, in addition to this, it's not easy to optimize or improve performance also. Optimizing the common case doesn't work. We're going to talk about principles in a little bit. Before that, I'm going to take a break. But you cannot think about common instructions, right? Some instructions take long, some instructions take short. You cannot optimize the design for the common case. You have to optimize your design for the worst case instruction because you have only a single clock cycle to deal with. So you need to optimize the worst case all the time. So let me take a break over here, but we're going to talk about microarchitectural design principles and how the single cycle microarchitecture violates that. So let's take a 15-minute break. So let's be back at 2:20. Okay, it's time to continue. Okay, so basically we've covered the single cycle microarchitecture, and hopefully I've convinced you that it's not a good idea. So we're going to look at better ideas. But before we go into better ideas, let's talk about some design principles that are really important. Remember, this course was about principle design, and there are 3 principles of design that's important for microarchitecture or architecture in general, but microarchitecture in particular because it's a relatively low level here. And these are critical path design, bread and butter or common case design, and balanced design. Now let's take a look at how the single cycle what these are and how the single cycle microarchitecture violates all of these principles actually. So the first one is critical path. Ideally, if you want to build a high performance processor, you want to minimize the critical path delay. How long is your clock cycle? That should be as small as possible. This makes sense because if you want to maximize performance, you have 3 levers. One of them is the clock cycle time, right? You want to minimize the clock cycle time. And basically you want to find and decrease the maximum combinational logic delay. You want to break a path into multiple cycles if it takes too long. So clearly we don't have this option in the single cycle microarchitecture, right? Single cycle microarchitecture has very limited gives you very limited freedom to minimize your maximum combinational logic delays, because that's really dictated by the longest time it takes to execute the worst case latency instruction. You can reduce that a little bit perhaps, but it's really long to begin with. You cannot say, oh, this is my clock cycle time. I'm going to ensure that this is my clock cycle time, and I'm going to make sure every instruction executes correctly given this clock cycle time. So if an add requires 1 cycle, so let's say, you cannot do this basically. You cannot say, I'm going to design a 10 gigahertz processor where the clock cycle time is, what is that, 0.1 nanoseconds, and design the system. That gives you, you're not as free as that, because your clock cycle time is really determined by the worst case latency of an instruction. You're not the one who sets that clock cycle time. It's the worst case instruction that sets the clock cycle time. If you cannot get that worst case delay to be less than 0.1 nanoseconds, too bad. And it's usually very difficult to do that, as I said, right? If an instruction requires many, many memory accesses, you're out of luck. You really need to have multiple cycles to be able to do that. If you have multiple cycles to execute an instruction, you can easily say, my clock cycle is X, and if an instruction takes longer than X, I'm going to make it execute in more than 1 cycle, right? It's simple. Okay, bread and butter, common case design is very important also if you're especially optimizing for average performance. You want to spend time and resources on where it really matters most. So you really want to improve what the machine is designed to do. So there are some common cases where the machine operates at, and there are some uncommon cases. For example, if you're doing some computation, if you're executing a program that never has a divide instruction, it doesn't make sense to optimize the divider, right? If you have a divide instruction. We didn't talk about divide, but divide is a very uncommon instruction in general. If your machine is doing a lot of add instructions, if most of your instructions, 99% of your instructions are add instructions, you should really optimize your machine to do the adds really, really, really fast, right? Does that make sense? Because your cycles per instruction, the second part of the equation, will be dominated by add instructions. And you would really like to minimize the CPI for add. But if your CPI for add cannot be optimized, then you have a problem. In a multi-cycle machine, you don't have that freedom again, right? Add instruction, you can make it really fast, but your cycle time is really determined by some other thing, which is the really long instruction, which may not be happening commonly in the common case. So we violate that principle. So common case principle is also very similar to Amdahl's law, although Amdahl's law poses it in a different way. You all know about Amdahl's law, right? Yes. So Amdahl's law says basically the thing that you do not speed up at some point becomes your bottleneck, right? For example, if your program is parallelizable by 50%, the maximum speed up you're going to get by parallelizing your program in the best way is going to be 2x, right? Because 50% is parallelizable. Assume that you put all your resource in it to make that 50% zero. That goes away, but you're left with the other 50%. Now your performance doubled, but this is your bottleneck now. The other part that's not parallelizable. Similarly, I gave you the example of add instructions. 99% of the time, if you're doing add instructions, you'd better optimize those. If you optimize the other 1%, then you're going to get at most 1%, right? If you optimize all of the adds, you're going to get 100x, right? Your 100 goes down to 1. So basically, common case principle is the same thing as Amdahl's law. You want to focus your efforts into the bottleneck. But the single cycle machine doesn't allow you to do that. And the third one is balanced design. Balanced design is also very important. And basically, this means that whenever you're designing a system, you want to have the system balanced. Now, what does this mean? This also has similarities over here, but in a different way. You want to balance the instruction and data flow through the hardware components. You don't want any part of your hardware to be your bottleneck. Balance the hardware for the work. This will become a little bit more interesting when we talk about multiple instructions per cycle. For example, if you design a machine that can fetch 10 instructions per cycle, we didn't do that yet, we are fetching 1 instruction per cycle, it doesn't make sense to not have enough functional units, right? Enough ALUs in the system. We will see that. We will see those machines very soon when we talk about GPUs, for example, or vector processors. We'll see examples of machines that can execute thousands and thousands of operations per second, per cycle, not second, per cycle. But you need to have a balanced machine to be able to do that. Another example of balanced design, if your system requires a lot of data from memory to go faster, and if you don't provide enough bandwidth from your memory, now that's your bottleneck. Your system is not balanced. Your processor can execute many, many instructions in a second, but your memory cannot provide enough data to those instructions. And today's systems are actually very prime examples of that. Today's systems are not very balanced because of how we design the systems today. As a result, we have this imbalance in the system. We're violating some principles in today's systems, consciously, unfortunately. Okay, but these are very, very fundamental principles, and actually, the single cycle design violates all of these principles. And I'm not going to go over this again. You can think about this yourself. I think I've given you the answer to this. Okay? So you should think about these principles whenever you're thinking about the design. Okay, I'll give you another aside over here, but This is going to be a little bit fun. I'll give you some examples if you're interested in this. So when designing good computer systems and architectures, it's important to follow good principles. And principle design was our first lecture for this very reason. Now we're back to it in lecture 12. And remember that I gave you this quote, right? Architecture design should be based on principle and not upon precedent. And clearly, single cycle design violates these principles, and that's why we're going to look at new principles, new designs. And this is just to jog your memory, right? This was a precedent-based design, maybe a single cycle microarchitecture, and maybe we'll go to a multi-cycle microarchitecture. That's of course the joke over here. The analogy doesn't work perfectly, right? Always. But I'll give you another aside. Basically, we will continue to cover some key principles in this course, and here are some references that you can learn more about these principles. If you're really interested, this is a very nice paper, a little bit outdated now. You can see that it's 17 years ago, but it talks about bottlenecks and some principles for microprocessor evolution. This is another paper that we're going to reference a lot. This is a little bit harder to read. The first one is very easy to read. The second one is harder to read. It was written in 1966. But we're going to get back to that when we talk about single instruction, multiple data architectures, because this has a classification of computer architecture designs in terms of how many instructions and how many data elements they can process. This is another one, Amdahl's law. We just talked about that, right? This is the common case design principle. It was developed by Amdahl in this really short paper. Okay, I think that's all I'll say about it, but you can take a look at that paper. And this is another one, actually, Hints for Computer System Design from Butler-Lamson. This is a very nice, this is more system level. It talks about how do you actually design a system in a principled way. So if you're interested, these are not required readings. These are all optional readings, but they will enable you to grow if you have time to look at them. So I'll give you a couple of design principles also. One is keeping it simple. And I'll motivate the multi-cycle microarchitecture using this. All else being equal, a simpler design is always better than a complex design. And even in cases where things are not equal, simpler designs are usually preferred over complex designs, because simpler designs are usually easier to reason about, easier to debug, easier to fix, easier to whatever, X over here. You can complete that. So simplicity is very important. And you may know this saying over here, everything should be made as simple as possible, but no simpler. Anybody knows who said this? Yes? No whispers? Anybody remembers this guy? It's Albert Einstein. And he definitely had the right mindset. And this is the mindset of an architect also. Things should be simple, but no simpler. And keeping it low cost. Low cost is also important in the system design. And we will see how the multi-cycle microarchitecture actually enables this. Basically, there's this saying, I may have said it in an earlier lecture, an engineer is someone who can do for a dime, for 10 cents, what any fool can do for $1, right? Apparently this was an American who said this. That's why the dime and the dollar. But you can translate it to whatever currency you're using. And for more, you can see Butler-Lamson. Butler-Lamson actually puts both of these as some of the fundamental, biggest principles in his paper over here, Hints for Computer System Design. Okay, so that's the motivation for multi-cycle microarchitectures. We want something intuitive, but we want also simple and low cost. And something we can optimize also. So something you can actually relatively easily optimize is another good principle. You want a design that you can easily optimize and fix. You don't want a very rigid design you cannot fix. Okay, so the idea is very simple, or the goal is very simple. Let each instruction take only as much time as it really needs. Actually, the goal, even the close to you can remove from here. The goal is really ensure that each instruction takes only as much time it really, really takes, not any longer. So the idea is you determine the clock cycle time independently of the instruction processing time. That's what I said. A designer says, I want a design that's going to run as fast as this one in terms of my clock cycle, and I'm going to ensure that it works. Now you should not have a single cycle design anymore. An instruction takes as many clock cycles as it needs to take based on the clock cycle that you've determined, which means that you have multiple state transitions per instruction. That's hence the word multiple cycles. And the states that are followed by each instruction is different. Essentially, we have a finite state machine, right? A finite state machine that executes the program, and you do state transitions across that, and you have many, many states. Okay, so remember the process instruction step. I'm not going to go through this in detail again, but basically, ISA specifies what the architectural state prime should be given an instruction in architectural state. From the ISA point of view, there are no intermediate states. One state transition per instruction, but microarchitecture, we have freedom. In a single cycle microarchitecture, we didn't exercise this freedom, but in a multi-cycle microarchitecture, we can do whatever we want as long as we transition architectural state to architectural state prime at the very end. So basically, that's the idea. Having programmer invisible states to optimize the speed of instruction execution. Yeah, multiple state transitions per instruction. So this was the single cycle microarchitecture. We're going to do this. In a cycle, we're going to go to another state. We won't change the architectural state, but we have some microarchitectural state, a programmer invisible state. And then in the next cycle, we're going to do something else. In the next cycle, we're going to do something else. And eventually, all of those something else will add up, and we will execute the instruction. And the final result will be the architectural state that the programmer expects based on the specification of the instruction set architecture. You saw the slide before, actually, in the previous lecture. Okay, so basically, let's take a look. This is the architectural state at the beginning of an instruction. To process an instruction, we're going to process part of the instruction in one clock cycle. Is it not done? We're going to process the next part in the next clock cycle. Is it not done? We're going to process as many clock cycles as needed to process that instruction. And eventually, we're going to produce architectural state at the end of the clock, at the end of the last clock cycle over here, architectural state prime. So let's evaluate this high-level idea based on the three principles that we just discussed. In terms of critical path design, this is beautiful because now you can keep reducing the critical path independently of the worst-case processing time of any instruction. Again, it's not dependent on the instruction. You can say, I'm going to have a 1 terahertz machine. And you're going to divide the instruction execution to these 1 terahertz, 1 over 1 terahertz chunks, right? Bread and butter design, now you can optimize the number of states it takes to execute important instructions, right? If an add instruction is really, really important, if it occupies 99% of your time, you say, I'm going to make sure this add instruction has as few states as possible to finish. We didn't have that option before. Balanced design, now you don't need to provide more capability than you really need in this case. You don't need to provide more capability or resources than really needed for a given instruction. For example, if an instruction needs resource X multiple times during the execution of its semantics, it doesn't require multiple X's to be implemented. Let's go back to load word. If you want to have load word execute, you need to access memory twice. You don't need 2 memories. You just have 1 memory. If you want to execute a branch, conditional branch, you don't need 2 ALUs. You can have a single ALU. You just compute the branch condition in 1 cycle, store it somewhere, and then compute the target address in another cycle, store it somewhere, and then update the PC based on those 2 results that you produced in different cycles using the same ALU. Okay? So this is actually very resource efficient in terms of cost. And I said this just now, basically. You can reuse hardware components that are needed multiple times for an instruction. We didn't have this luxury in the single cycle machine. That's why we had multiple ALUs. That's why we had multiple memories, multiple instruction memories and data memories. So of course, with any idea, I'd like to give the downsides of this also. Any idea has upsides and downsides. That's why this is the science and art of trade-offs, as we've discussed. Clearly, the upsides here are a lot. But we also have a downside. And the downside is really in what I've defined earlier. You need intermediate results, which means that you need to store them somewhere. It's not just your architectural state anymore. You have this microarchitectural state that you need to keep track of. Every cycle you produce some microarchitectural state, you need to store it somewhere so that you can use it in the next cycle, right? And this could become a lot if your machine becomes complex. So that's the downside. So the downside of this is hardware overhead for additional registers. So we cannot just have program counter, instruction memory, data memory, and the register file. Now we need to have intermediate registers. And we'll see that when we start designing this machine in a little bit. And unfortunately, this comes at a cost of performance also. It's not just area overhead, it's not just additional structures. Now, part of your clock cycle time is gone because every time you need to read from this register or write to this register at the beginning and end of the clock cycle, some part of it is going to be gone to this register set up on hold time overheads, right? And you need to pay that multiple times for every single instruction. That's the downside. So if your clock cycle time is actually really, really small, this overhead becomes really high. So you need to be careful when you're actually reducing the cycle time for your clock period. And we will see this when we talk about pipelining. There's some lost time that's just paid for reading from the registers and writing into the registers, these intermediate registers. And if you reduce your clock cycle time to be too short, the useful work that you're really doing in your clock cycle gets dominated by this. That's why reducing your clock cycle time a lot, or minimizing your clock cycle time, is not always the best idea. Now, if you do that, if you minimize your clock cycle time a lot, your cycles per instruction clearly increases, right? It increases because you need to have multiple cycles per instruction, because you need to do the amount of work, but it also increases because of this overhead. So it increases not linearly, but superlinearly. That's the unfortunate part. That's why the cycles per instruction and clock cycle time, they almost always go against each other. Whenever you're improving your clock cycle time, you give up on cycles per instruction. That's the trade-off. And you need to balance that trade-off to design a really good machine. Now it becomes really, really interesting. All right, it's not a simple optimization problem. You cannot just keep minimizing the clock cycle time. You need to be very careful as to what happens to cycles per instruction. Okay, so this brings me to the performance analysis. It's exactly the slide that I showed you in the last lecture. Basically, we need to be careful. We're really optimizing this equation. We're assuming number of instructions is constant right now. If you actually take a compiler's course, if you actually take an algorithms course, you should always think about, oh, those actually change the number of instructions. But now we can optimize average CPI and clock cycle time. So single cycle microarchitecture, multi-cycle microarchitecture, let's take a look. As I said, single cycle microarchitecture CPI is 1, because that's by definition. Clock cycle time is long, not so good. As a result, this runs like a dog and nobody builds it. Multi-cycle microarchitecture, CPI is different for each instruction. Average CPI is hopefully small. So if you're a good designer, a good architect, you make average CPI as small as possible by focusing on those bottlenecks. So you go through the biggest bottleneck, and then something else becomes a bottleneck. Now you optimize that instruction. And then something else becomes a bottleneck. Now you optimize that instruction. Eventually, hopefully, you optimize a lot that there's no single big bottleneck. Everything is relatively equal, and your improvements will not be as high if you do a big improvement. Okay, but the clock cycle time can be short in this case. But I've given you already that if you make it too short, your CPI may increase a lot. Okay, but the good news is we have 2 degrees of freedom to optimize independently. So let's take a closer look into this multi-cycle microarchitecture. We're going to design it. We're going to design one example of it today, and we're going to design another one tomorrow. The one that we're going to design tomorrow is introduced by this person. Does anybody know who this is? Well, I guess you can read it. This is Maurice Wilks. He's famous for designing many, many computers, but he's really the father of microarchitecture, if you will. He invented multi-cycle machines, and he came up with an elegant implementation of it, which is micro-coded or micro-programmed machines that we're going to talk about tomorrow. We're not going to talk about it today, but we're going to give you the concept of multi-cycle microarchitecture today. And you can see that he was very confident that this was the best way of designing a computer. It's a beautiful way, but I'm not sure if it's the best way at the moment. But the key idea for realization of a multi-cycle microarchitecture is one can implement the process instruction state as a finite state machine that sequences between states and eventually returns back to the fetch instruction state. So a state is defined by the control signals that are asserted in it. So the control signals really define the state. That's what you're doing in this state. It could be fetch state number 1, and then there could be a fetch state number 2, fetch state number 3. It could be the decode state. It could be the address computation state for a load instruction. So you have many, many of these states. Control signals for the next state are determined in the current state. So we're going to see why this is the case, because you don't want the control signal generation to be part of your critical path. Now you have another level of freedom, actually. In a multi-cycle microarchitecture, in this state, you can do the data path processing, but also generate the control signals that are needed for the next state, so that you don't have to do that processing for the control signals in the next state itself, which will lengthen your critical path. We will see this pictorially in the next lecture. So basically, this is going to be a state machine. We're going to replace this with a state machine. You're going to have a fetch state in the beginning, and then we're going to branch, and then the last states will always bring us back to the fetch state. Okay. So in a basic multi-cycle microarchitecture, we already said this instruction processing cycle is divided into states. A stage in the processing cycle can take multiple states. So let me go back to the previous slide. This is the processing cycle. There are 6 stages. These could be multiple cycles themselves, or multiple states. So this could be 6 times 3, for example, or it could be imbalanced, right? For example, the evaluate address can take 10 cycles. It depends on our design. A multi-cycle microarchitecture sequences from state to process an instruction. And the behavior of the machine in a state is completely determined by the control signals that are asserted, or that are set in that state. And the behavior of the entire processor is fully specified by the finite state machine. Essentially, your finite state machine is your processor. So in a state, control signals control 2 things. One is what the data path should do to the data, how the data path elements should operate, exactly like what we've discussed in the single cycle microarchitecture, but also how to generate the control signals for the next clock cycle. And we're going to see that with an example now. Okay, you guys are ready? Let's do another example. Good. So this is our single cycle MIPS processor. Remember, this is our single cycle. The multi-cycle is going to look very similar, except we're going to add registers here. For example, later I'm going to show you that there will be a register here, there will be a register here, there will probably be a register somewhere here, ... Why? Because we're going to be able to do multiple cycles. We're going to read the instruction from the instruction memory, latch it. That's our cycle. And then in the next state, we're going to decode the instruction, read the register file, and latch the results. That's another cycle, ... Okay. So let's actually go through this relatively quickly. We already said this over here, but if you look at the multi-cycle MIPS processor, you have 3 adders and 2 memories. That's a lot. Now we're going to look at a multi-cycle microarchitecture that's going to be much better. We already said some of these, but we're going to reuse the expensive hardware on multiple cycles. We're going to reduce the number of adders, we're going to reduce the number of memories. But the downsides, as you can see, we already said this over here. But we will go through the same design steps. We need to design the data path. Now our data path needs to be able to store intermediate data, and we need to design the control for it. Control will be a finite state machine. Okay, so what do we want? Basically, in the single cycle architecture, there are 2 memories, one for instructions, one for data, as we've discussed. We want to use a single memory. Single cycle architecture needs 3 adders, ALU, PC, branch address calculation. You can look at the microarchitectures that we designed. We want to use the ALU for all operations. We want a single ALU, single memory. Of course, we've already discussed this. Every instruction takes 1 cycle in a single cycle architecture. We're going to break that over here. We're going to divide the instructions into multiple steps, and simpler instructions are going to take fewer cycles. So let's take a look at the load word instruction, and we're going to start designing the multi-cycle microarchitecture using the load word instruction. So this is what we need to do for load words. And you've seen this already before. We need to read the instruction, we need to read register from the registers, we need to get the immediate value to calculate the address, we need to read the memory from the contents of that address, and we need to write to the destination register. So simple. We've already gone through this multiple times by now, actually. So how do we design the multi-cycle data path? Let's break it into some stages. Right now, we're going to, there are actually a lot of principles as to how you should break things into stages, but we're not going to, how you should break things into different stages, different clock cycles. What you should do in a clock cycle, we're not going to concern ourselves with that at the moment. Maybe when we go through pipelining, we're going to go into it a little bit more. But the first step is fetch instruction, and this is our data path for it. The PC needs to go into the instruction memory, and instruction memory provides the data, in this case the instruction, and we're going to latch it. That's it. So we've just added a latch. That's the difference from the single cycle architecture, right? We have this intermediate register, which was a big no-no in a single cycle microarchitecture. That's the first step. The second step, we're going to read the register. And to be able to read the register, you need to be able to supply this thing that I cannot read, the instruction. Basically, this is the ID of the register that's coming from instruction bits 25 through 21. After the read, we're going to latch the result that we read from the register file, another intermediate register. And to be able to compute the address, we need to be able to have this data path elements. You've seen this already before. And to be able to do the calculation of the ALU, this is what we need to do, essentially. Okay? We want to get the data from here, and then do the addition. We need to latch it. Okay? Now this can be done. This can be done in one cycle. This can be done in one cycle. This can be done in one cycle. Now we have 3 separate cycles, right? And at the end, we have the address to read from memory. As you can see, the control signal is the same, essentially, right? We had this address calculation logic in the single cycle design as well, and the control signal was exactly the same, except they're going to be asserted at different cycles now. Okay, now we have the address. What are we going to do with it? We're going to access memory. We've eliminated the other memory. This is only one memory, instruction/data memory. So we need to provide a mux such that we can select the address coming from the back end of this design, coming from the ALU output, the latch at the end of the ALU output, such that we can access the memory. And in this cycle of processing, 1, 2, 3, 4th cycle of processing of the load instruction, we should take the address to feed into instruction data memory from this input of the mux. So now your control signals are dependent on which state you are in. That's what I exactly said a few slides ago, right? Now you can read the instruction/data memory with the address that is produced by the load instruction, and you get the data and you latch it again. At the end of the 4th cycle, step 4, we have the data read from memory latched into this register, this intermediate register. Now the last step of the load is taking that value and writing it into the destination register. So your destination register ID comes from this latch over here, and the thing that you're going to write, the value that you're going to write to the destination register comes from this latch over here. This was produced at the end of cycle 4. In cycle 5, this gets written, and you need to set the right signal over here. Now we're done. This is the data path elements that you need for executing a load word instruction. Makes sense, right? 5 cycles. But we're not done yet, sorry. There's incrementing of PC. Never forget incrementing of the PC, otherwise you'll be stuck executing load word, right? So you need to add this data path also. Now if you want to use the same ALU, you need to make this part of the data path complicated, right? So basically this is an example where if you want to increment the PC, let's say you do this in the next cycle, cycle 6 of processing. You need to take the program counter, you need to go through these muxes that you need to add so that you can actually increment the program counter by 4. And the result needs to be supplied back into the PC over here. And you need to orchestrate the control signal such that in cycle 6, this operation happens. Make sense? But now we don't need a separate ALU for branch target address computation, right? For PC+4 computation, or a separate adder for PC+4 computation. We're using the same adder, but at different cycles. At cycle 1, no, it's not cycle 1. I think it's at cycle, let's see, 1, 2, 3 over here. We use that adder to do the address computation. In cycle 6, we're going to use that adder. We're using that adder to do PC+4 computation. Much simpler. We have one memory, one ALU. For store word, you need to do something else. You need to provide the path for after reading the data. So store word is very similar to load word. Hopefully you're familiar with that by now. You actually got the data from the register, and you need to provide a path to write it back over here. That's essentially the path you need to execute store word. And the control signals are essentially almost the same as single cycle microarchitecture, except there are certain different cycles. Okay, and this is R-type instructions. You read from RS and RT, and this is the path, the additional path that you need. You need to be able to read from RS and RT. Remember that these are encoded in different places in R-type versus I-type instructions. That's why we need these muxes. And then you need to be able to write that result back into the register. So you need to provide these data path elements. And this is branch equal, and you can study this. Basically, you need to provide these additional data path elements to be able to execute all these instructions. That gives you more muxes, more wires, more ... and control signals. But I'm not going to go through this. You can study this. The principles are very similar to single cycle design. And that's what we have at the end. This is our complete multi-cycle processor. This is the control logic. And control logic, if you look at it, it's very, very similar to what we've designed earlier. So let's take a look at the control unit. Control unit is this, basically. We have an opcode, and we have a main controller. Let's call that it's a finite state machine. Every cycle, this produces a different set of control signals, because you're sequencing through execution of a single instruction. A single instruction goes through different stages. Different stages map to different sets of states in this finite state machine. But let's build this finite state machine relatively quickly. Essentially, it's a finite state machine. So the first state is the fetch state. When you reset the computer, you go into the fetch state, and you have initialized PC and registers. So the fetch state fetches the instruction and puts the result into this register. This is called an instruction register usually. Now at the end of the state, you unconditionally transition. Well, okay, these are the signals that you need for this state to work. And you can convince yourself by going through this. Clearly, you need to read the instruction over here. You need to write the instruction register. You need to write the PC, ... These are the signals that are asserted. I'm not going to go through this in detail, but it's kind of obvious what you're doing over here. But the key thing is you need to write to this register. And some of these are X's, as you can see, because we're not doing anything in that part of the pipeline. Clearly, when we're fetching an instruction, we're just exercising this part of the pipeline plus the control logic. So in the next state, we unconditionally transition into the decode state in the finite state machine. And that has another set of control signals associated with it. I'm not showing you the control signals, but that essentially generates the control signals over here. And you can see that at the end of the state, we jump to a different state depending on the opcode. So there's a conditional transition to this state or some other state or some other state. We will see that as we build this finite state machine. So if the opcode is load word or store word, we're going to jump from the decode state. Decode state actually decodes the instruction. And it gives you whether you should jump to this state or some other state. Let's assume that we jump to this state. This state is memory address computation state. You have another set of control signals that need to be asserted. As you can see, this part of the data path is exercised. Okay, in the decode state, let me go back. Let me pull back over here. This is the decode state. Here, this part of the data path is being exercised. We're actually reading the register file. We're putting the data into this latches over here. We're actually doing the sign extension, ... Everything over here is happening still. At the end of the clock cycle of the decode state, you have the registers that are read inside this register, right? And then we're going to use that in the next cycle. And if the instruction happens to be load word or store word, this is what we're going to do. The states will be associated with these signals. ALU source is coming from A over here. ALU source B is coming from 1, 0, which is this mux, this input of the mux. Because remember, we need, for load word or store word, we need the base register, which is the first register over here, plus sign extended immediate. And ALU computation should be addition. And at the end of this state, this cycle, the data gets latched into this register. Makes sense? So it's basically a state machine. And we could keep doing this. The next state over here is the memory read state. The next state over here is the memory write back state. So in one cycle, you read memory. In one cycle, you write the result back to the register file. So you need to set the associated signal. So I or D means, are you reading the instruction or data part, depending on how you design the memory. And this part is, are you writing to the register or not, and where are you getting the data from. So these are the signals that you need to control the data path correctly for the execution of this particular state. And if you actually go through the state diagram, if the opcode is store word, there's a conditional transition over here. If your opcode is load word, you do this. If the opcode is store word, you jump directly into writing to memory, right? Now let's go back. If your opcode happens to be R-type, after the decode state, you jump into this set of states. If the opcode happens to be BEQ, you jump into the states. And every state is different, and it's defined by the control signals that are associated in it. And this is our complete multi-cycle controller. And you can keep adding. If you need to add another instruction, you just need to add more states, as long as you have the data path elements and control signals. And you could keep adding, jump, for example, and that brings us to the end of the lecture. So that's essentially your finite state machine for a multi-cycle microarchitecture. And I'll see you tomorrow with the multi-programmed architectures.